Okay, hello guys. So today we will be seeing that how to find out the stresses on a shaft when it is being subjected to a different combination of the loads. Okay, so before that, let's play a game. Right, that game will be like this. Suppose we have got a shaft. Okay, we have got a shaft, and if I say that I will be applying an axial load on it, means it will be acting along the axis, right? And I will be also saying that its cross-sectional area, it is your A, okay? And then I will ask you that what is the magnitude of the stress acting on it? You will be very happy and you will be saying that, sir, it will be sigma T is equal to P by A. Nice, tensile stress. I will not be surprised on that. Yeah. So it will be all about your tensile stress, right? Suppose if I say you, let's increase the level of the game. On this shaft, if I am going to apply a bending load acting at a point from the point A, so point B, distance x. Now tell me, what is the stress acting on it? You will be saying, sir, it's very simple. It will be your sigma B, means the bending stress, means the bending stress, okay? And it is all about your what? MB y by I. So MB is what? MB is all about your bending moment, okay? And this Y is distance from the neutral axis of what? Neutral axis of what? Of the outermost fiber. Of the outermost fiber. Okay, and suppose if it is a shaft of the diameter D, then your Y will be your D by 2. And I is all about your moment of inertia. Perfect. Okay, you will be very happy to answer all these things, right? Now I'm saying that let's do one thing. Let us give a torsional moment to the shaft by let the moment of this the magnitude of this moment be empty. Okay, now what is the stress acting on it? You will be very happy, and we say that sir, it will be having the shear stresses which is equal to mtr by j, where r is the radius and j is your ip, that is your polar moment of inertia. You will be very happy to answer all these things. I'm also glad in that case. But now I will increase the level of the game, right? And I will say that suppose what if I will put an axial load on it and I will put a bending load on it. Say the moment of the bending is your MB and this is your P, okay? And the cross-sectional area as always should be A, right? Okay, that's it. So now it means what? That suppose it's the shaft, I am going to pull it out as well as bending it. Pull, bend, right? In that case, what will be the stress acting on it, right? So for that thing, you have to think that what are the different types of stresses we have studied in Zoom or in MOS, okay? So it will be just a quick revision for you all that stresses, it can be of two types: the normal stress and the shear stress, right? In normal stresses, we do have two types. First one is axial stresses and the bending stresses, okay, right? And in shear stresses, we do have only one type of stress, that is your pure torsional shear stress. Perfect. Okay, now what we have to see in this thing, these normal stresses can be operated in a simple algebraic method. Algebraic method, right? Means what? They can be added and subtracted in a normal manner. In a normal manner. Okay, in a normal manner, right? But what about this shear stress? No, it can't be. So we have to deal this in some other way. Okay, so let us first see off that what is in this diagram. Here I have told you that this shaft has been subject to the axial and the bending. Okay, right? So here we have the 2 points, say A and B. Our final object, it will be somewhat like this. Okay, right? And this is all about your neutral axis, right? Now we see that the fibers, those who are above this neutral axis, are being subjected to the tensile stresses, and the fibers which are below this neutral axis are being subjected to the compressive stresses. Okay, fine, done. So we can add the axial load and the bending load. Okay, so at A we will be having the tensile load, and at B we will be having the compressive load. Okay, so we see that it can be added by P by A plus MBY by I. Okay, fine. And at B it will be your P by A minus MBY by I. Okay, fine. Why? Because due to this bending, we have the tensile load at A, and we have the compressive load or the stress at the B. So it will be your minus, it will be your plus. Fine. Now I will say it's okay. Very good. Let's play one more game. Why don't we apply a torsional stress to it in the form of empty the torsional moment, right? In that case, we can modify this equation as follows. Suppose if we have got out here this stress and this one, right? This is your P, this is your MB, and this is your MT. Okay, so we have the axial load as the sigma A. Okay, it will be your P by A. We have the sigma B as the MB. Sorry, it will be your MBY by I. And if we have the tau, that is your MTR by J. Now we have to get it combined. Okay, in that case, I hope that you all have studied in so the principal stresses. Yes, so we will be having the two principal stresses. One will be your maximum and one will be your minimum. Fine. Okay, so here we can have the sigma A plus sigma B plus by 2 plus square root of sigma A minus sigma B by 2 the whole square plus tau square xy. Okay, and minimum is what? Sigma A plus sigma B by 2 minus square root of sigma A minus or plus, sorry, minus only sigma B by 2 the whole square plus tau square xy. It's a way to find out the maximum and the minimum principal stresses. And suppose if you are asked to find out that what is the maximum shear stress acting on the shaft, in that case, we will be simply taking this part. So it will be all about your square root of sigma A minus sigma B by 2 the whole square plus tau square xy. So in this way, we can find out the combination of the stresses or the net stress due to the combinations of the different types of load, axial, bending, and torsional load. Okay, fine. So I hope that it might have got in your mind, right? Now we will solving one numerical on the same. Okay, so we see out here that a shaft is shown below. Okay, is subjected to a bending load of the 3 kilonewton, and we have got the pure torque of 1000 newton meter and an axial pull of the force that is your 15 kilonewton. Okay, so we have to find out the stresses at the points A and B. Okay, it's very easy question, right? Okay, so we will go in a sequence wise. In the case that we have been given out here, W is equal to 3 kilonewton, so it will all about your 3000 newton, right? And T is given as 1000 newton meter, that is your 1 into 10 to power 6 newton mm. Fine. And the load which is acting on it in the axial direction is the 15 kilonewton, so it will be all about your 15 into 10 to power 3 newton. And here the dia is given as the 50 mm, right? Okay, and the x distance from the point, from the fixed point, that is all about your 250 mm. Fine. So now we have to find out, first of all, what is the cross-sectional area of the shaft. Cross-sectional area of the shaft. Okay, so it is all about your A is equal to pi by 4 t square. So it is pi by 4 into 50 the whole square, that will be your 1964 mm square. I hope that you can find it by yourself, right? Okay, so now we have to find out, first of all, what is the tensile stress. What is the tensile stress due to axial pull at points A and B? Okay, fine. We have to find out that, right? So in that case, we can find out by sigma. You can say for the axial is equal to P by A. That is all about your 15 into 10 to the power 3 by 1964 as we have found out, and this is all about your 7.64 Newton per mm square. Okay, or we can also write 7.64 megapascal. So I hope that you all might have found out the tensile stresses at A and B. So it will be the same, right? Now we have to find out the bending stress at A and B. It will not be the same. No, it will not be the same. The bending stress acting at A and B will not be the same. How we can find out? See, suppose we can find out bending moment at A and B. It's what? M is what? W into X. Okay, so this is the bending load, that is all about your 3000 and into 250, that is your 750 into 10 to the power 3 Newton mm. Fine. And now the section modulus of the shaft. What is this? We have seen that in the bending stress we have got the formula mby by I. Means we can write it like this, mby I by y, right? So this mb I by y is all about your z, that is your section modulus. Okay, so here we can find out that z is equal to your pi by 32 into t to the power q 3, right? And this is your pi by 32 into 50 q. And if you get it calculated out, it will be coming as 12.27 into 10 to the power 3 mm cube. Okay, right? Now therefore the bending stress at A and B is what? Sigma B is equal to m by z. So it is all about your 750 into 10 to the power 3 by 12.27 into 10 to the power 3. So it will be all about your 61.1 MPa. Okay, Now we have to see that what will be the nature of this bending stress at A and B. Okay, and at A it will be your tensile, and at B it will be your compressive. So we have to act accordingly in the same way. Okay, fine. So now we know that here we have one tensile stress is also acting on it. Okay, right? So we have to find out the resultant tensile stress at point A. It is your sigma A is equal to sigma. You can say that the bending stress that we have found out plus the tensile stress. Okay, it's A or O like that. It's saying. Okay. So it is 61.1 plus 7.64, because here we have got a net tensile stress acting on at A, so we have to get it added up. Okay, so it is all about your 68.74 MPa. Okay, and now at B we have the compressive stress. Okay, as I have explained before, we have the sigma B is equal to the sigma B minus sigma O. Okay, so it is all about a 61.1 minus 7.64, that will be your 53.46 MPa. That's all. So in this way we have found out the bending stress acting at A and B. Okay, why? Now we have to find out what is the shear stress acting on it. Okay, so we know that the shear stress at point A and B is what? Due to the torque acting on it is tau is equal to 16T by pi d cube. This equation that we might have studied in SOM, right? So it is all about 16 into 1 into 10 power 6 by pi, and the d is your 50, so it is cube. So your answer will be coming as 40.74 Newton per mm square, or 40.74 MPa. Perfect. So now we have all the types of stresses acting at the points, right? Now we have to find out the combination of these stresses, right? As I have explained in my first slide. For that, we will find it individual at the individual points. What are the stresses acting? So the stresses at point I'm fine. I'm sorry, my net had gone. Okay. Okay, fine. So where were we? We have to find out now the stresses. Okay. Right. Okay. So we have got the stresses at the point A. The stresses at point A. Right. So it's what? Maximum and minimum. What? Principal stresses. Okay, in the short form. Okay, right? So here it will be the sigma A. Max is what? Sigma A by 2 plus square root of sigma A by 2 the whole square plus tau square. That's all about that equation, you know, to find out the maximum and the minimum principal stress. Okay, and for this we can do sigma A by 2 minus square root of sigma A by 2 the whole square plus tau square. Okay, and we have seen that sigma A value is your 68.74 by 2 plus square root of 68.74 by 2 the whole square plus 40.74 the whole square, as we have found out in the form of the axial bending and the shear stresses. Likewise, value we can keep it out here 68.74 by 2 minus square root of 68.74 by 2 the whole square plus 40.74 the whole square. And eventually we can find out here it is as 87.67 MPa, and here it is your minus 18.93 MPa. Okay, we have to keep one thing in the mind out here. If this value is positive, maximum at A means what? It will be your tensile stress. And if it is negative in the case of the A, means it will be your compressive stresses. Okay, reverse will happens in the B. If at B you will find the stress with the negative sign, it will be your tensile. The positive sign, it will be your compressive. Okay, so let us find out that what actually the stress at the point B. Before that, what would be the shear stress at A? The shear stress at A. So obvious, it will be this part of the equation, right? Means the square root of sigma A by 2 the whole square plus tau square. And if we keep the respective values inside it, we will get the shear stress value as 53.3 MPa. Perfect. Okay. Now we will see that what is the stress acting at point B. Okay. So we have got out here the stress at B point, right? Here we will be having the maximum one and the minimum one. Okay, fine. So we see that the sigma B max is what? Sigma B by 2 plus square root of sigma B by 2 the whole square plus tau square. Now to be very sure that how we can find out the minimum one, for that one we will be having the sigma B by 2 minus square root of sigma B by 2 the whole square plus tau square. Right, and if we keep the respective values inside it, we will be getting it like this, plus square root of 53.46 by 2 the whole square plus 40.74 the whole square. And here we will keep the same thing, but our sign will changing, right? So it will be minus. Out here we have to mind all these things, otherwise our questions may go wrong. Okay, right? Now the respective values that we will be getting out here is 22 MPa, right? Okay, and for the sorry, here we're getting 22 MPa. Okay, and here we will get at 75.46. The answer out here will be negative. This shows that this 22 MPa is your tensile. Why? Because it is in the B1. So the B1, so the B part, the maximum stress, the maximum principal stress that we will talk about is your compressive. And at A, the maximum principal stress that we will talk about will be your tensile. Okay, fine. So it's all about that, right? And again, if we are told to find out the maximum shear stress, then it is this part of the equation. Okay, and then we can find out by keeping the respective values. Thank you all for watching my videos. Thank you very much.